Welcome to this video. Today, you are going to learn about how to set up a computational aeroacoustic simulation through an example case, which is the cavity noise problem. These are the main steps to be followed to configure your simulation setup. Although they are common for CFD, determination and selection of some parameters differ in CAA. You have already learned the types and properties of these steps in the previous modules. Today, we will focus on how to select them for a specific problem. To do this, we must first check the features of the problem, such as its expected flow characteristics and the resulting noise spectrum. Then, we must also check the features of the flow solver, such as what kind of numerical schemes and grid types it has. Let's apply these steps to the noise problem arising from a deep cavity geometry at relatively high speeds, which are encountered in weapon-based. First, we should understand the flow problem by literature review. Literature says that deep cavities are exposed to highly unsteady and complex turbulent flow fields around them. The incoming turbulent boundary layer separates from the upstream edge and directly impedes on the aft wall, which causes acoustic waves propagating upstream and then results in an acoustic feedback mechanism. Here, the shear layer breakdown composes broadband noise, whereas the feedback mechanism generates intense, narrowband discrete tones, called Rossiter modes. Now, based on these flow and noise characteristics, we can determine the simulation approach. Considering the previous modules, capturing a broadband noise due to a high Reynolds number complex turbulent flow requires a high fidelity simulation. This means we need to solve the Navier-Stokes equations. Next, we need to select the turbulence modeling and resolving approach. Although DNS is the most accurate option, it is restricted to 2D low Reynolds number flows. LES is able to capture 3D high Reynolds number flows at a reasonable cost. However, it is too expensive for this kind of wall-bound flows, where there are multiple walls in each direction. RANS or URANS approach fail to capture broadband noise. The most appropriate options in terms of cost and accuracy are the hybrid methods like wall-modeled LES and delayed detach edge simulation. DDS is chosen here. Let's continue with the selection of grid generation parameters. Before starting, we need to check some properties of our solver. Suppose it is based on a second-order accurate discretization on structured grids, and it has a second-order accurate explicit time scheme. These parameters are available in most of the commercial softwares. In addition, what we know about DDS is that it models eddies inside boundary layers and resolves the rest. This implies that boundary layers should be meshed according to the RANS criteria, and the rest should be treated by the LES criteria. Now we can start choosing the grid parameters along the wall normal direction as shown on the slide. The non-dimensional wall normal distance, y+, should be approximately 1 when starting meshing from each wall surface. The subsequent grid nodes can be created with a maximum stretching ratio of 1.2, which is typical in RANS regions. The stretching ratio should be reduced to 1.05 within the LES region, and maintained up to the maximum cell size, delta max. No further stretching should be applied until the LES region ends, where turbulent activities are no longer seen. In the Euler region, the stretching ratio can be gradually increased to 1.2, which eventually provides some mesh damping for non-reflective boundary conditions. Because cubic cells are preferred in LES regions, streamwise and spanwise grid spacings are also chosen to be equal to delta max. Now it's time to choose delta max. There are two aspects to consider for this selection: turbulence and aeroacoustics. In turbulence aspect, typical CFD grid dependency studies should be employed to check some criteria such as mean profiles and energy spectra, resolved and modeled turbulent energy ratio, and 2-point correlations. For hybrid runs LES and wall-resolved LES approaches, which are mostly used in CAA simulations, the last two criteria are the most critical. It is highly recommended to follow the references given here when evaluating grid resolution in LES regions. In aeroacoustics aspect, which can be the most decisive factor for broadband noise estimations, delta max should be set such that high-frequency sound waves are properly resolved. In this sense, delta max can be simply limited by the formula shown on the slide, where we need to know our maximum desired frequency, Fmax, and the minimum number of mesh spacings needed to resolve one way, defined here as A. It is not easy to obtain the exact value of the parameter A for nonlinear high-order partial differential equations. Instead, a dispersion relation of derivative of any function is usually used to get an idea. The figure on the right compares the dispersion relations obtained by different numerical schemes, which shows how much of the wavelength can be resolved with a single mesh. Since our solver has a second-order accurate spatial scheme, we need at least 16 mesh spacings to resolve a wave properly. If we used a fourth-order dispersion relation preserving scheme, for instance, A would be 5, which highlights the importance of a high-fidelity numerical schemes for CAA simulations. Let's continue with the selection of time step. In turbulence or CFD aspect, CFN number is the typical condition to be satisfied. Although implicit or dual time schemes can relax this criterion, large time steps can ruin the gains from the spatial scheme. For LES and DES studies, there are other time step criteria. One of them is that non-dimensional time step based on friction velocity and viscosity should be around 1 for regions where the ADs are resolved. For further guidance, please read the references given here. In aeroacoustics aspect, time step is limited similarly as in delta max. Besides Fmax, the minimum number of time steps that is required to capture one wave determines this limit. The parameter B is chosen by looking at the dissipation and dispersion characteristics of a model equation, obtained by different numerical schemes. For a second-order explicit time integration, we need at least 5 time steps per period. The simulation is started from an initial flow field, which can be set by either free-stream parameters, mean profiles, or a steady-state run solution. The last option would accelerate the process, during which the initial transients leave the computational domain, and the mean flow field reaches a statistically stationary state. After that, the simulation can be continued by activating the DDS option. Since a fully turbulent boundary layer is expected to separate over the cavity, boundary layer transition has no influence on the noise generation mechanism. Therefore, any runs turbulence model without a transition model should be sufficient for this problem. Next, boundary conditions are chosen as shown in the figure. Since our solver performs discretizations on structured grids, we need two separate blocks for the inner and outer domains that communicate with each other along the shear layer by any multi-block strategy. An important point here is that a sponge zone or non-reflective far-field boundary conditions should be applied at the upper and side faces of the outer domain to ensure that the generated acoustic waves leave the domain without any reflections. The simulation is ready to start. Before starting, we also need to specify data sampling parameters for post-processing, which usually includes application of an acoustic analogy and estimating sound levels. Acoustic analysis requires a lot of data, which results in a large memory usage. Hence, the sampling parameters should be selected wisely. Here, we focus on the most common ones: the sampling time step, which is chosen according to Fmax, and the sampling period, which is chosen to cover the period of the largest wave. Some useful relations that will help to select these parameters are given on this slide. Note that For an accurate spectral estimation, sampling frequency Fs and the frequency resolution delta F must be sufficiently large and small, respectively. In this video, you have seen the steps to follow for a CAA simulation setup. These steps have been applied to a cavity noise problem with the help of the theoretical information provided by the previous modules. Lastly, I would like to show some of the results obtained from this example simulation based on our selections. The figures, other than the multi-block grid views, are typical aeroacoustics results that you need to analyze. The sound level spectra reveal the generated broadband noise with the tonal register modes as expected. Besides, overall sound pressure level distribution indicates the region that contributes to the total pressure energy at most, which can be useful for optimization. Also, plotting Q criterion isosurfaces always helps to analyze the motions of the turbulence structures. Thank you for watching this video. I hope you enjoyed it.